This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. Welcome everyone to the third in a series of 4 lectures on genome assembly, de novo genome assembly. Last week, you remember I talked a lot about the general recipe for doing de novo genome assembly and some of the things we need to think about and some of the problems we may encounter, including the bane of our life if you do genome assemblies, the repeat unit in genomes. And talked a lot about some computational requirements, perhaps, about what it's like to do that many alignments when you've got millions and millions and millions of reads, and the kind of computational hit you can have from them, and that we needed to come up with a better way. This week we're going to go into a lot more detail about the some of the algorithms, one in particular, and that's the Brown graph assembly algorithm. All right. So to start with, just a bit of a recap. Obviously, in an ideal world, I'll be able to point a magic wand at people and pull out their entire genome. But we don't live in the Star Trek universe, so I can't do that. So now at the moment, we don't have a machine that is capable of taking a single piece of DNA and telling us every letter with 100% complete accuracy in that single piece of DNA for the whole replicon or a whole chromosome at a time. They're just too big and they're too fragile, and the machines can't cope. In the case of some of the algorithms, the chemistry that they use to sequence the reads breaks down after a while, and so it just stops working. And in others, the machinery itself is quite harsh on the DNA and wobbles it around too much, and the DNA just breaks. It just falls apart. And so for now, in the real world, we have to take our single pieces of DNA, our chromosomes, our replicons, our whatever they happen to be, and we have to break them down into smaller pieces to be able to read them. And we can do that either enzymatically or with a sonic probe, ultrasonic shearing or something. All right, and then we send all these little pieces off to the sequencing machine, and they go and sequence them for us. And then they come back with FASTQ files, which are the sequences of each of those little pieces and the associated quality, or what the machine, how well the machine thinks it did at reading those pieces. And a bit of a recap on lengths. Illumina generally between 100 and 300 base pairs. Iron Torrent, which you're seeing less and less of nowadays, but is still around. We still have a few machines here at the university, are between 1 to 400 base pair reads. PacBio, 40,000 plus base pair reads, but they are quite error prone. And then Oxford Nanopore, I think there was a 2 megabase read. So 2 million base pairs in a single read, quite error prone though, about 10% error. All right, de novo genome assembly is the process of taking all of our millions and millions of random short pieces that we know the sequence of and trying to reassemble them, trying to jigsaw them all back together into this original piece. But instead of just being some pretty colours on a screen, we now actually know what the sequence is. We know what the letters are in each position along this nice coloured thing, because we know the sequences of these, and we've hopefully jigsawed it all back together beautifully, and we now know the sequence of the top. All right, ideally we get one sequence per replicon after we've done our assembly. In reality, this doesn't actually happen. The process that we use for doing this is called, well, after we've done the laboratory stuff and read the reads, the process of taking them and building our contigs is overlap, layout, consensus. So we find all the overlaps between all of the reads in a pairwise manner. So this one versus this one, 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 and so on and so on and so on, until we've covered every combination of pairs. And then we lay them all out. And the way we lay them out is we build a graph in computer memory. So we have a list of all the reads and all of their connections to all the other reads. And in overlap layout consensus method of doing it, the reads are the nodes in the graph, and the edges in the graph are the connections or the overlaps between them. And then by finding a Hamiltonian path through that graph, we can walk through the graph and find consensus contigs. And if you remember, we did Shakespeare and Yoda last week, trying to figure out a way of finding the overlaps and laying them out and then pulling out a consensus sequence. And the way we build an overlap graph is like this. So here are our reads. We found the overlaps. So the purple read overlaps the red one and the blue one. So we add them both to the graph. We add all three of them to the graph. The purple one gets added, the red one, and then we draw the edges in. And these edges represent the fact that they overlap. And this red one overlaps the blue one and the green one. And this light green one overlaps this dark green one here. And then to find a path, a Hamiltonian path through this graph that visits each node once, we start here and go there, 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 and there. And that will give us our, excuse me, that will give us our contigs at the end. Now, before I move on, does everyone remember what the word contig stands for? It's a contiguous sequence that we've reassembled. It may not be the complete chromosome, but it's a draft or plausible piece of sequence that we've managed to rebuild out of our reads after we've run our assembly. Right? It may not be correct, it may not be the full sequence, but it is a possible sequence. Hopefully, it is much, much, much longer than each individual read. All right? So we've run our algorithm, we've come out with our list of contigs. They're our possible sequences that we can find from our assembly. All right, some problems that we have when we do these assemblies. Read errors, introduce false edges and nodes into our graph, false connections, non-haploid organisms, so heterozygosity causes a lot of little bubbles and edges and things in the graph, and that can make our life difficult when we're trying to find a path through it, and repeats. So if they're longer than the read length, it's impossible to resolve them. It's impossible to find out where they belong in the genome. And I think I talked about that ad nauseum last week. And this is the reason why. When the computer goes to find the overlaps between all these red reads and all these yellow reads, it says, yeah, look, they all overlap. Even because they're a copy, the original DNA is a copy of one another. So all the little reads from there will all overlap one another. And so the computer lumps them together and we get this bit here. And so when it walks through to pull out contigs, we get 1, 2, 3, 4. Okay? And that's because none of those reads span the repeats. And they cause problems in our graph. And this is a real graph from I think it's from a Salmonella assembly with 300 paired end base pair reads from Illumina. And long reads, because they actually cross the repeats and they anchor the repeats on either side, we can determine whereabouts the repeats live in our genome, and so we can place them exactly and we come up with one contig. So if we have nice long reads that are longer than our repeat lengths, then yes, we can solve our repeats. Oops, wrong way. And I talked a little bit about this. So with 250 base pair Illumina for $200, we can get those list of contigs on the left. And with $2,000 on a 10,000 base pair reads out of the pack bio machine, we can get a single chromosome and a plasmid, nicely circularised, etc., for bacteria. However, if you've got to sequence 300 bacteria in a week, it's going to cost you a lot of money. So it's a lot easier to multiplex a single Illumina run and pay, maybe $1,000 on an Illumina machine to do 300 bacteria and still get the information you need out of it, rather than have to go down the path of trying to find $100,000 a week to run a pack bio machine. All right, so that was a recap of what happened last week. Now we're going to talk a little bit about assembly in detail. We're going to go through a couple of different algorithms. So the first one we're going to talk about is called the greedy extension model. And so this is a really old one. It was one of the first ones they came up with, and then they found there was a whole bunch of problems, so they kind of dropped it. But the first thing we needed to do was compute all of the overlaps between all of the reads. And that, if you think about it in terms of doing alignments on each one, they were doing full alignments on each one, and so it's kind of like ON squared times OL squared, and so as the number of reads increases, the compute complexity squares, and the same thing with the read length. And so we have lots of trouble. Well, it's fine if you've only got a couple of hundred reads, but if you've got 15 million reads, it becomes very, very difficult to do. But anyway, this is what we used to do back in the old Sanger days, when we probably only had 40 reads or so to work with anyway. And then what we used to do was we just find the longest overlap and join them together. So the longest overlap we have here is 200, so we'll just join them together and make them, now they're one read. And then we start again. And we say, all right, the next longest overlap is between here, and we'll just join those together. And then, oh look, this bit here and this bit here overlap there, and so we'll join those together, and hey, presto, we've got our nice contig out of our 1, 2, 3, 4 reads. However, there's a couple of problems with this. Sometimes this 200 overlap could have happened by chance, and in reality it should have been the 50 that we used first. All right, and so this piece here may actually better fit this other end of the 4 here. All right, so sometimes it makes globally optimal decisions rather than locally optimal decisions, this algorithm. Sorry, wrong way around. It makes locally optimal decisions rather than globally optimal decisions, and can sometimes lead to misassemblies because of the fact that the repeats can cause it to say, oh, look, there's a beautiful overlap here, where it's just overlapped the repeat rather than overlapped the bit that it should have overlapped. And so things fall apart rather quick. It's okay if you've got up to about 10,000 reads, you can run it in a few days on a computer. However, if you've got over 1 million reads, it just doesn't scale at all. And so this quickly fell out of favour once more and more reads started coming online. This greedy extension method started falling out of favour, and then more and more people started finding issues with it, doing misassemblies. And so it was dropped pretty quickly. So our problem with all of these reads doing this overlap layout consensus thing is that there's just too many alignments to do. Right? And remember from your alignment talks a couple of weeks ago now, it's actually computationally expensive to do a fuzzy alignment where you allow for gaps and mismatches and things like that. Right? So all of this is all alignments. It's just too hard. It's just, if you have a large range for the minimum and maximum overlap size, and if you allow 97% identity between the overlaps compared to 100%, it changes the amount of computation you have to do. And so we needed a better way to handle a lot of data, because these Illumina machines, the early ones, even though they're only doing 36 base pair reads, they were still spitting out millions of reads in one go, and we were like swamped. Everything just broke. We didn't know what to do anymore. Anyway, I'm going to talk a little bit about why they thought that getting short reads might help. Before Illumina was invented, has anyone ever used a microarray? I know I'm showing my age a little bit, but there are such a thing called microarrays, and basically they are just little plates that have certain little pieces of DNA stuck to them. They're only single-stranded pieces of DNA stuck to them. And what you do is, if you had if you had a sample of DNA, you'd break it up, and then you'd wash that over, and anything that hybridised or anything that stuck, so anything that was a reverse complement to the bits that were stuck on these plates, you had all these little things sticking off the plates, anything that stuck to them because they matched, right? And then they would add a little fluorescent tag to it, and so then they'd flash lights on it and then look at the glow, and then they'd say, all right, so that spot there's glowing, and that is spot number 64, which represents this sequence, and so we must have the reverse complement of this sequence in our sample because something stuck there and made it light up. So they had these little plates where they could say, all right, well, we kind of know that these little bits of sequence are kind of important for some experiment, and so we'll put all of those onto a plate and we'll wash our sample across and we'll see if anything sticks. And if anything sticks, then we'll know we've got that particular sequence in our sample. All right. So what they thought, well, hang on a minute, what if we put every single possible sequence on a spot on one of these plates and then washed our sample across, and then everything that lights up means, hey, we've just found all of the samples or all of the sequences that are present in our sample. Okay, so that's what they did. It was proposed in about 1995. They put all possible k-mers, so remember, each position in a sequence can have 4 possibilities, A, C, G or T. Can't have any others, so there are a definite number of permutations that we can have. Obviously for 20 to 25 length sequences, the number of combinations or the number of permutations is actually quite high. And so, but they could put all the possible k-mers on a chip, chop up our target DNA, heat it up enough so that it splits apart, and then add some fluorophores onto the end of them, and then flood it onto our chip and see what sticks. That's the hybridisation step. And then measure the fluorescence on each of these spots on the chip. And then that will give us a list of all the k-mers that are present. Well, that's pretty cool, because suddenly we know the sequences that are present in our sample out to a length of about 20 or 25. So if k equals 5, there's 1,024 possible 5-mers. Oh, that picture in the corner there is actually what you get back from a microarray thing. So here they all are, our 5-mers, all A's, all the way through to all T's. Put them all on a chip, hybridise the target DNA, measure fluorescence, make a list of the 5-mers that are present, and for each pair of 5-mers which overlap by 4 base pairs, so an exact match, make a link. So basically what we're doing is we're taking the last 4 of one k-mer and the first 4 of another k-mer, and if both of those appear in our list of k-mers that are in our sample, then we'll just assume that they would normally overlap in our sample. All right, and so we're going to link them together. And so if this k-mer here was found in our sample and this k-mer here was found in our sample, we've just assumed that the k-1 length that's in exact match between these two is an actual overlap. And so we just said, yep, this now 6 long sequence is in our sample. And then we'd find the k-1 overlap with another one and say, yep, there's 7 length sequences in our sample, and so on. And so if we can link all of our samples like this with the k-1 suffix and the k-1 prefixes from all of these little k-mers that we've found, we can build a graph of what that looks like, and then a path through that graph will hopefully give us back our original sequence. And so if we had this sequence to start with, okay, and we chopped it all up in a few different hundreds of copies, etc., chopped it all up randomly, and then flooded it onto our chip. And these were the spots we got back. And then, so they represented these k-mers. So as you can see, this A quadruple T here exists in our sequence, and so it's one of the in our list. It's quadruple TC's there, this TCCAG's there, etc. And so if we can just find where all these suffixes match all these prefixes exactly, we've just built connections between all of these bits, and we're looking for exact matches. We're not looking for weird alignments where we've allowed mismatches and gaps and things. We're just doing exact matches, and that is a whole lot easier computationally to do. And there's no alignment, right? It's just say, does this equal this? In fact, it's even easier to do in a computer because you can just say, you can use a hashing algorithm and it will automatically tell you whether or not it's there. And you can take all these connections and build a graph. And so that's what they did. And this was the graph they came up with for our previous example. So our sequencing by hybridization graph, the sequence on the previous slide for k equals 5, and the nodes on this are the 5-mers, and the edges are overlapped by 4 bases. And then they thought, wow, this is cool, we can just follow a path through this graph and pull out our original sequences. And we can go all around this loop and pull up all this nice stuff and come out here and pull all that out. It's a ripper. We can just, every time we go to a new node, we just add the last base on to our growing sequence. Isn't this beautiful? And then they got to here and went, ugh, what do we do here? Which path do we take? Uh-oh, we're in this problem again. We're in that problem where the computer is either going to have to start making stuff up or we're going to have to stop. Because we're scientists, we don't make stuff up, so we have to stop. And so they followed it to here, they followed this beautiful path all the way to here and said, oh, which way do we go? We don't know, we'll stop. Okay, and then they started, well, it kind of works, didn't it? Kind of. But it was a really good idea, because suddenly they could add lots of information into the graph really quickly without having to do all those alignments. But of course there were millions of practical problems with this. Running microarray technology and trying to fit that many spots on a chip was very problematic to start with. It relied on a whole bunch of weird chemistry that kind of worked, and at high GC content, the GCs would stick to anything. Right, so yeah, it was a bit of a nightmare. And obviously, k-mers for k equals 5 aren't really unique. There are, imagine that the chances, there's only 1,024 of them just by literal chance. Those sequences are going to come up again and again and again and again in our graph. And because they're not unique, you can almost say that they're going to be repeats, and we're going to have lots of little hubs and spokes in our graph, which is very difficult to resolve. The number of spots we need on a chip is 4 to the power of k. So if we want 32 mers, which is round about where we're starting to see uniqueness in our thing, we need 10 to the 18 spots on our chip, which is just way too many. The people who were running that technology at the time just went, yeah, nah. Okay, and then cross-hybridization is a problem, so anything with high GC would just stick to everything and bugger everything up, and not all the k-mers would hybridize equally. So some of them would have a little spot, and it would only fluoresce a little bit, and you'd say, is it actually present, or is it just cross-hybridization, or I don't know, is it just weak hybridization? We don't know. So, but the algorithm behind the technology, the assembly algorithm, the bit where we just added these things called k-mers to a graph and look for exact match overlaps, that was a really good idea. Right? The actual sequencing technology itself wasn't that great, but the idea behind the assembly was a really good idea, and so they took that and ran with it. So we came up with the Brown graph assembly. I'm not sure if I've ever told you the story, but that's pronounced Brown. I was in a conference in the Netherlands, and the grandson of De Brown was actually in the conference, and someone from the EBI was going on and on about these De Bruin graphs. These are graphs, these De Bruin graphs, And the bloke from about the third row yelled out, "It's brown!" And it was the head of the EBI that was giving the lecture. So now, because Ewan's been told off about it, everyone has to say brown. All right. So de Bruijn graphs are just an abstract mathematical construct. They're a directed graph. Nodes in the graph are k minus 1 mers, and the edges represent the k-mers. So I know it's kind of weird. The overlaps are actually the nodes, and the k-mers are the edges. So this node here is a k-mer, 110, and this node 100 is an overlap. And this edge here, if you add that 0 to that 110 there, you'll get 1100, because from travelling from this node to this node, what we're doing is we're adding on a 0. So this edge here represents 1100. And this edge represents 1000, because when we travel from here to here, we're just adding on a 0. And from this one to this one, we're adding on a 1. So this edge here represents 1101. Does that make sense? It'll make a whole lot more sense when we're not looking at numbers, believe me, all right? But basically, if I walk a path through this graph, I can pull out any sequence of zeros or ones. And in fact, if I follow this path through this graph, I can pull out the sequence 111000 by traversing this edge and pulling out that k-mer, and traversing this edge and pulling out that k-mer, and then this edge and that k-mer. And you can see that they're all n minus 1 overlaps. So this is n equals 4, so they're length 3 overlaps. Okay, so this 110 matches with this 110 here. Okay? All right, so then the full sequence is 111000, which I get by moving through this graph. Okay. All right, so now I just need a little bit about why we want to use k-mers in the first place. When we need this de Bruijn graph, everyone thought, oh, this is a great idea. Let's do this. It's so easy. It's going to make our lives so much better because we're just going to find the exact matches of n minus 1. But what happens when you've got some reads that are 200 base pairs long and some reads that are 100 base pairs long? Now we're in trouble, aren't we? Because how do we find the exact match of 199 overlap when the other read is only 100 long? We can't, it doesn't work, right? And so to be able to use the de Bruijn graph to do an assembly, we need all the sequences to be exactly the same length. And so they came up with another idea, hey, let's just find all the k long subsequences of every read, and we know what k is, and therefore we can, as long as k is shorter than our read length, our smallest read length, it'll be fine, because then k is the same in every case, and we can build a de Bruijn graph. And sometimes, if we're looking for exact matches, the read errors will mean that it's not an exact match and we'll get a misconnection, right? But remember, in Illumina reads, the 5' end is usually pretty good and the 3' end is usually where it starts to fall apart because of the chemistry. And we know that the first part of the read is usually generally okay, and the last 10 to 15 bases has got a much higher probability of having an error in it. Well, what if we set our k length to just shy of that region? We could pull out all the really good information out of our reads, right, and still use this read that has an error in it, but it could still be used in our assembly because we can just pull out the bit of the read that's good and leave off the bit that has an error in it, or the bit that has an error in it won't affect our graph too much, hopefully. Okay, all right. All right, we're going to do a k-mer de Bruijn graph. We're going to build one. And so we've got some reads. We've got this Happy, Pine, Innes, and Appen. So they're our reads. Now, they're different lengths, aren't they? So we can't do n minus 1 overlaps because they're all different lengths. There's some that are, well, most of them are 5 long, but we've got one that's 4, and that's going to screw us up. So we can't just say, all right, find all the 4 overlaps and we'll be happy, because it won't work, okay? So what we need to do is we need to find all of the subsequences. And in this case, let's try 4, because that's our smallest read. So let's just find all the 4 subsequences for each of these reads. And so we'll do that. And so this happy here, our 4-length subsequences of that are hap, the first 4 letters, and then we move across 1, and then we pull out the next 4 long subsequence, which is appy. And so we get those 2 kamas out of there. Pine is already length 4, so we just use it. And ines, we can get 2. We can get ines and nes. And then from appen, we can get appy and pepin. All right, and so then we can uniquify them. Oh, isn't that perfect? All right, we can get unique kamas. So we've got happy, pine, pepin, ines, and nes. All right, so let's build a Brown graph out of those. All right, now what we want to do is we want to find the k-1 exact matches. So we want to find where hap matches. Is there another hap on any of the suffixes on any of the other reads or any of the other kamas? Or we want to find, is there an app, which is the prefix of this read? Does it appear in any of the suffixes of any of the other kamas? And look, this app here is exactly the same as this app here. All right, so maybe we're onto something here. Maybe we can do this with exact matches. So the way we do it is we take the first kama and we break it into a k-1 prefix and a k-1 suffix, so HAP and APP. And then we add them both to the graph, if they're not already there. So we don't have anything on our graph at the moment, so here we are, we've added them in. We've got hap and app. Right, and then we know they're connected, so we add an edge to the graph connecting them, and we label it as the kama, because that's what produced these 2 subsequences, this suffix and the prefix. All right, so that's the first read, or the first kama. Now we'll do the second kama, appy. Now, we split it into the 2 pieces, and then we look, hang on a minute, this app already exists in our graph. We don't need to add it again, all right? And so we do need to add PPI because that's not there yet. So we'll add that. There, like that. Okay, so here's the next step of our graph. All right, let's take the next kama, pine. So let's repeat it. So let's go. And pin and ini neither of those exist in our existing graph here. So we need to add both of them and draw a line in. And you'll notice it's not connected to anything, it doesn't really matter. That's okay. And the next one, pepin. So we're going to have PPI and PIN. Luckily for us, they both already exist in our graph, and so all we need to do is draw in the connection. So we do, draw in the connection and label it. And then inners, there's INE already exists, but NES doesn't, so we add it in. And we do the same for NES. And there we have our completed graph. So this is pretty obvious what it says, I hope. Now, it's actually what we need to do. So here's our completed graph, and our next step is walking through the graph to pull out our finished config, our finished assembly. All right, so let's do that. But to be able to do that, we need to know where to start, because we could. Where do you start when you start looking for things? We start on the top left because that's how we were taught to read. It's like convention, right? But what if that HAP was down here, right? Because it's arbitrary, right? But what we look for is we look for an unbalanced node. We look for a node that has no inputs but an output perhaps, or in this case, this one has no outputs but it has an input, so it's unbalanced. Whereas all of these ones have inputs and outputs, right? So these are balanced nodes. And so we start at an unbalanced node with degree not equal to 0, and we walk through the graph and we add the edges as we go. And stop when we hit another unbalanced node. An unbalanced one is where the number of inputs and number of outputs is not equal. So we'll start with the first one, hap, then the next one, appy, this, and it spells happiness. All right, so we just assembled happiness, and hopefully we walk away happy. All right, now that was really easy, yeah? But that's the algorithm. That's exactly what we do. All right. Pretty simple. However, so, yeah. Yeah, there is possible there's a loop, and I'll show you an example in about 15 seconds. But the first thing I need to talk about is this kind of traversal where we move through the graph like this, where in this, what we want to do is we want to visit the edges, because they're the important things, right? We want to visit each edge once. We don't care about how many times we go through a node, we just want to visit each edge once. All right, and so it's called an Eulerian work. I can never pronounce that word, but Euler. He was a famous Greek mathematician, did some cool stuff, and someone named a walk after him. All right. A directed connected graph is Eulerian if and only if it has two semi-balanced nodes and all other nodes are balanced. That means we have a start place and an end place, and we have a path that can visit each edge once. The graph is connected if each node can be reached by some other node. So sometimes we build graphs and there's completely separate parts. Remember when we first started building this graph, we had that little 3-node bit and then we added another 2-node bit, but there was no connection between them. And so they're connected if only if they can reach everything. And an Eulerian work visits each edge exactly once, and it's much easier to find this computationally than a Hamiltonian path. However, not all graphs have Eulerian walks, and sometimes you can start going down a path and then hit a fork in the road, and then so you have to stop. But that's okay, because we've just assembled part of it, and we've built a contig at least. All right, and here's this, hopefully will answer your question. So a semi-balanced node is one that only has, that has no inputs. So an unbalanced node just means they're not equal. So the inputs are not equal to the outputs, whereas a semi-balanced node means it's either missing completely inputs or missing completely outputs. Does that help? All right, so problem of repeats. Now, because we're humans, we can look at these three reads and probably piece together what it says because we have context, right? And we have our prior knowledge of things and a giant river in America, right? However, the computer doesn't have prior knowledge of a river in America. Or if it does, it has it in a completely different context and not the context that we're looking at here, which is genome assembly. And so we just get these reads here. And so we're going to do our same thing. We're going to split them up into k-mers. We're going to take our wonderful formers again. And so missus becomes miss, issy, and cis. Lots of s's in this. And then sissy becomes cis, cis, and issy. And you'll notice that this is different to this is. And this one becomes sippy, becomes sip, sip, and ippy. And then when we find all the unique ones, we get these. So what we're going to do now is we're going to take all of these k-mers and we're going to build the graph like we did before. Let's start with the first one. So miss, we split it into two, the prefix and the suffix, and label the edge as the k-mer. And then we'll do the next one. There's no connection there. And then there's sip. And you'll notice that in this case, this SSI is the suffix for this one, sorry, the prefix for this one as well. So it already exists in our graph, but there's a different suffix. So the prefix already exists, and the suffix is different. And so now we have a choice path here. And we add in the next one, issy. Oh, cool, that joins our two bits of graph together. That's nice. And the next one, I'm tipping, is going to be a problem because the suffix ISS exists over here, and the SIS, the prefix, exists here, which means there's going to be a connection across there, and we're going to have a loop. Does that answer you? We can get loops. and then we add the other two, and we get that. Okay, so now, can we find a path through this graph that visits each edge only once? Can we do it? Can we start at a unbalanced node, which is this one here, and bugger. We can get to there. Don't know which way to go, but if we go this way, we've got to go through that edge again. That's no good. If we follow this path, we miss these two edges completely. All right. There's no Eulerian path, because if we were to go around this loop and come back down and go here, this edge here would be visited twice, and that breaks our rules, so we can't do it. And in actual fact, just by building this graph from our unique k-mers, how do we know how many times to go around this loop? Do we go around once? Do we go around 50 times? Is it the Mississippi River, or is it the Mississippi River, or is it the Mrs. 15,000 times Mississippi River? We don't know, right? And the computer certainly doesn't know. And so we just don't know where to go. And so what we need to do is we can pull out contigs. So we find an unbalanced node here, and then we start and we walk through until we hit a point here where we've got to need to make a choice and we can't go any further. So we add these two k-mers together to get one contig. And then we can get these two k-mers together to make another contig, and then these three k-mers together to make another contig. Does that make sense to everyone? How we got these contigs? Okay, and that's, even though we know, right, we know it should say Mississippi, there's not enough information in our reads to say that it should be Mississippi. We're missing a k-mer. Yeah.
Is this, if you did this again, would you get the same config every time, or would you do 3 different configs?
If you had the same k value, you would get the same graph.
You get the same graph, right? When you're building those 3 configs, could you not have just built this, and then, so the first 2 blocks to get a config, and then the next 3 to get another config?
You mean like that, over there? Oh, the first one here, and then started from here and gone around the loop? Yeah, I guess. But our thing says keep going until you find a fork in the road. And so they were our rules that we decided upon, and to build the graph, yeah. And so that's what makes it consistent more than, yeah, of course you can. You can start anywhere you like, but the rules that we kind of made up at the beginning says start an unbalanced node, walk until you have to make a decision. All right, what would happen if we changed the value of k? So this was done with a value of k of 4. Let's change it to a different number. Let's try 5. So these are all the 5-mers. So let's build the graph out of this. And when we do, we get this. We get Miss and Issy, we get Missy, and etc. And it loops around again. And then we have a separate piece that there's no connection between. So we've increased our value for k, and suddenly we don't have a connected graph anymore. All right? Damn. We've made one of our contigs longer, maybe. We've made one of our contigs 1 letter longer. So the first contig now will be Mrs. with an extra S on it. But suddenly we've broken our connection here. And so when we use the Brown graphs to do an assembly, the choice of k is really, really important, because sometimes we can get, with much lower k values, we get all these little disparate pieces all connected together. But unfortunately, we get lots of little loops. Now, sometimes we can get rid of the loops just by making the k-mers longer, and that'll remove some of the ambiguity in our graph, but at the price of making it suddenly be disconnected. Right? We'll have less connections in our graph. And so that can be a problem. And so we need to choose k wisely. Right. So With a lower K value, we get more connections, so the graph is more connected because it's more likely that things will overlap at exactly K minus 1. But there's less chance of resolving the small repeats. We're going to get more loops in our graph. But we'll have, because there's more k-mers coming out of each read, we'll have higher k-mer coverage, which matters a little bit later on. It also uses more RAM. I had someone decide to try a K value of 19, and they had 32 million reads of 300 base pairs, and so that made a lot of k-mers, and then they tried to fit all of them into RAM, and the computer went, no, that's not going to work. Whereas they could run it on the same computer with a K value of 63, no worries, because it didn't produce anywhere near as many k-mers. Higher K value will have less connections in the graph. So we saw when we did our Mississippi, we increased our value of K from 4 to 5, and suddenly the graph was disconnected. So at higher K values, we'll have less connections in our graph. But maybe we'll make K longer than our small repeat, and if K is longer than our small repeat, what happens? We can span the repeat, and we'll remove a loop out of our graph. Right? But we'll have lower k-mer coverage, which may be a problem, may be a benefit. Come on, go away. And the optimum value for K will be a balance of these two effects. And for the 4 people who came to the tutorial at 8 o'clock this morning, we talked about that quite a bit. And so the tutorial tomorrow and Friday, or the 3 tutorials to go, tomorrow and Friday, we're going to talk about that. And we'll actually do some assemblies with different values of K on the same data set. We'll all do a slightly different one, and then we'll compare them and look at the way the patterns involved and how the different values of K affect things. All right, so on Friday I'm going to start with what happens when you add errors into the graph. But for now, I think I'll stop here. Cool, thanks. Yeah, so the tutorial is actually doing assemblies and comparing the outcomes with different values of K to see what happens. Sorry, that's my throat. Is that all right? Cool.
So one thing that you mentioned is that increasing K reduces the number of k-mers?
Yeah, because if you have a read this long and the k-mer size is this, you'll get there.
Oh yeah, the number, the actual number. Okay,
Yeah,
the actual
but
number.
then the chances of getting unique k-mers, the number of unique k-mers might also increase. And it's the number of unique k-mers that are the ones that you actually have into a hash table.
You make them a lead first.
Yeah, and so if you've got to fit 15 million reads into a hash table rather than 10 million reads into a hash table, it's going to use less RAM and etc.
Most of the language sometimes that actually fit in memory, so using JSONs, lists, and graphs.
Hey. Yeah. Oh, okay. We don't have a whiteboard in here, do we? I don't have any paper, unfortunately. Yeah, okay, cool. I'll print some off here. Okay, so if we have our read of length, say, I don't know, 300, right? Our read's 300 long, and we pick a k-mer size of 31. Right, we're going to have that one, and we'll have that one, we'll have that one, we'll have that one, we'll have that one, and that one, and that one. In fact, we're going to have 268 unique. Well, there's 268 cameras out of that one read. Okay? All right, because we take every 31 base pair subsequence out of there. Every single one of them. And if we have our read has got 300 and our camera size is 150, so 151, right? So that's 300, and this is 151, and there's going to be that one, and that one, that one, and that one. In fact, here there'll be, I don't know, what did I say, 268 cameras or 269 cameras, and in this case there'll be 148 cameras. And so, just in the fact that, and they're all unique, right? There may not be any repeats in here, whereas in here as well, they may all be unique. And so here we're going to have that many cameras to represent this one read, and this many cameras. But if you've got 15 copies of this read, multiply 15 by 268 versus 15 by 148, right? There's a whole lot more coverage in the cameras than there are in the reads. Does that make sense?
So those more unique.
There's more unique cameras, yeah. And the unique ones are the ones we have to add into the graph.
Oh, I see. And it prevents.
Yeah, well, hopefully, if we can make these cameras bigger than our small repeat size, right, then it'll span the repeat, and we won't have that this as a natural fact. If we had a slightly longer read, in K equals 7, perhaps, we would have, that loop would have disappeared out of our graph. We would have had a nice, smooth path through it. Does that help? Cool.
Thank you.
No worries.
Just one question. So, what if we just start with a large K like 5 and lens, if we find something is not connected and lens we try like force in some unbalanced, is it possible to do that?
If you think about it a different way, right?
Yeah.
So you know how we had these, if we had it, they're all the same length, right?
Yeah.
If we had have had these and just use them, like this SSIS, actually no we can't because it doesn't, no there are no connections between these, so it won't work. We have to break them up to find connections. There's actually a missing read. If there's one, we had one more read which spans this little bit here, we would have been able to remove that loop and span that gap, but unfortunately it just didn't work. Yeah, so but yeah. Yes. So if we start at 5, there's a break, and then we add 4, and we go, look, there's a connection, and then you can go back to 5 to maybe solve the repeat. There's a class of assemblers that will do exactly that. And what they, so the one that we use in our little tute tomorrow and Friday is called Velvet, and it chooses a single camera and builds an assembly. Right? And if we do it lots of different times, we can see the effect that K has on the assembly. However, there are some assemblers, like the one called Spade, which actually assemble it with a low Kmer value and a high Kmer value. So they assemble with a high Kmer value to get rid of the loops, and they assemble it with a low Kmer value to connect different bits of the graph, and they can find parts of the graph in this one and parts of the graph in this one are the same, and then they can say, oh cool, these two bits that weren't connected are suddenly connected. And so they can draw that connection in on the meta graph, right? And so they combine Ks for different graphs to build a better picture. But no one knew about that in 2007. That was only a 2014 edition by a bunch out of Russia that came up with it. Yeah. But anyway, good thoughts.
So there is no way to get some previous knowledge of how long is the sequence?
Yeah, you can. There is a way, and that involves taking the DNA out of the cell and stretching it out and putting it on a ruler. And I'm not joking. But that's what they do for some of these things. They actually measure it by stretching it out and seeing how long it is. Yeah,
I
yeah.
think that's an important features of the sequence.
Yeah, and in actual fact, they do that for a very good reason. Is that they can kind of chop it up, right, using an enzyme, right? So and if